Thank you, everyone. I'm Henrik, and I'm going to tell you about neuroimaging. So first, a bit of background. More than 10 years ago, we started on a bold quest for AI. But I'm not really going to tell you about AI. Rather, I'd like to share a couple of the lessons that we've learned along the way. The first lesson is that we need to study real intelligence to figure out AI. That means studying brains. The second lesson is a lot less obvious, and it is that the brain is not a computer. If you think this is obvious, you probably don't know that computers really represent almost everything we know about, except for brains. And we have to reject this idea that computers will be able to do what brains can do. It's not about the right algorithm or about more computing power. It's about figuring out how the brain is different from computers and building that. But in any case, these two lessons tie together in an interesting way, because current neuroimaging techniques look specifically for the computer. And in the process, they throw away most of the information as if it was noise. So we end up with something that looks more like this than what is actually there. So let's look at the ingredients of a better solution. First of all, we treat the recorded information as a hologram, because holography literally means taking the whole information. We combine this with a recent paradigm shift in signal processing called compressive sensing, which is able to reconstruct resolution information far beyond what was thought possible, by simply assuming that what we're reconstructing is not noise. Then we leverage our understanding that the brain is not a computer to look beyond its electrical circuitry and instead look at the electromagnetic flow of energy. It's important to understand that the energy doesn't flow in the wire or in the circuit. And this provides a much richer picture. And importantly, directly reveals how different areas influence each other. Because if energy is flowing from A to B, that means A is influencing B. And this is something that is actually there. It's not based on statistics like it's currently done when building causal connectivity maps. Finally, to make all this work, we need a lot of computing power. And we started out up here in the middle doing 2D reconstructions, and now we are up in the corner with full 3D reconstructions. We plan to skip this step and move directly to the cloud so that we can deploy and scale fast. With cloud power, we'll be able to reach the full potential of our method in terms of increasing resolution and visualizing the resulting data. So let's look at where we are now. We start out with the raw data recorded at the red dots here and a model of the conductivity of the brain. Before I show you our prototype, I just want to flash through what the competition looks like. So try to keep these pictures in mind and compare with what you're about to see. So this is a video of our first prototype showing for the very first time electromagnetic energy flow in the brain at millimeter resolution with 1 million voxels, which are 3D pixels, and 1 million particles showing the flow dynamics. This new view of the brain will provide a completely new understanding of how it works, as well as much improved diagnostics and targeting and tracking of therapeutics. An interesting aspect is that with the same technology that we use for imaging,